autonomous navigation using centralized intelligence will introduce themselves and explain how they have done the work. Thank you.
Thank you, Professor. Yes, so autonomous navigation using centralized intelligence is our project. Here's just a basic outline of what we'll be going through today, everything we'll be touching on. And to meet our team, there's a picture of us, we're here too. Team leader is myself, I'm Andrew Bonin, I'm the project manager and hardware lead, electrical engineering student, and most interested in control systems engineering.
I'm Michael, I'm the software lead and interested in the machine learning aspect.
I'm Oscar Rowe. I'm a computer engineering major. I'm the hardware and software support, and I'm interested in database systems.
I'm Jack Popovic, and I'm a career engineer. I'm the firmware lead on this project, and I'm interested in hardware-software integration.
All right, so project motivation. As discussed earlier, with the continued advancement of technology, there is a big increase in autonomous vehicles. It's actually projected by 2030 that there will be around 28.8 million autonomous vehicles on the roads, and it will just be increasing. Also, manual driving is not the safest. There's many accidents, collisions. So our motivation for our navigation system would be from the need for a new and efficient navigation system that can benefit from the upcoming technological era of autonomous vehicles and V2V communication. Who is affected? If it becomes a standard, then it would affect anyone on the road. It could also be used for various situations, such as giving priority to emergency vehicles in certain situations, such as with ambulances or fire trucks. Here's just a picture of a world with smart navigation as its standard. On the left, you can see just some V2V and even V2I infrastructure, and then on the right is an example of the emergency vehicle warning system.
So for our project selection, we looked at the current ways that companies are implementing these, and most companies are going with decentralized networks, so each car would have its own intelligence and would communicate with other cars without a centralized server. So our idea was to actually have a centralized server so we could actually implement more computing power to handle the large amounts of data coming in, and also to handle and also to make recommendations to all the other vehicles on the road so that they could plan their paths better as they navigate throughout the environment. So this is a breakdown of our project summary. So the first part of our project summary is to actually be able to find a microcontroller that can handle all the data that we'll be inputting into it. And we are still looking for the right microcontroller, but we went with Arduino for this specific demonstration. And then we had to decide which kind of vehicle we were going to use to actually implement the hardware onto. So we went with, we were going to buy one off of Amazon, but we decided to go with a 3D printed one so that we could actually choose where our sensors were going to go and design the models to actually have all the sensors in the right locations. And we also simulated the project on Carla. So Carla is, we'll talk about it more later on, but it basically allows us to simulate self-driving cars and all the sensor integration with the cars. And so the final part of our project, we hope to demonstrate it on a track, and the track that we will be using will be similar to the one that we use in our simulation in Carla. We hope that this will help us to actually be able to demonstrate it, a physical representation of our project rather than just the simulation portion.
Some design requirements and specifications, just some general system requirements. The smart navigation system will need to be generalizable to different roads, maps. We don't want it just to be overfitted or just for one environment. That will just require a lot of training. It should also be able to take into consideration of priority vehicles, as I mentioned earlier. It needs to be implementable into current vehicles. That would be optimal, and it would be needs to be user-friendly. And the system has to have safety requirements met with encryption and authentication.
So this is our engineering marketing trade-off matrix. Safety is obviously our #1 concern because vehicles, when they're driving at high speeds, they become dangerous when humans are controlling them. So our artificial intelligence will have to be able to avoid collisions in a way that a human will be able to trust the vehicle. So, and also, as you can see, security and safety go hand in hand. We plan to use encrypted channels to communicate the data to our centralized database and also to all the other vehicles.
So yeah, this is our little objective tree we made that shows how we split up every individual goal that we had. So at its core, we're trying to create a smart navigation system that's split up into 4 subsections, each in namely such as simulation, Dragonfly setup, which is our local positioning system, our database setup, and our physical implementation. Each of those has another subsection on how we're going to go about it. To simulate, we will be setting up Carla, which is a vehicle simulation software that we can use due to its sensor library, so we can actually physically implement it. For the Dragonfly setup, our local positioning system, we plan to create a path planning algorithm using input data. Our database setup will be to create a updating table on MySQL, which based on the input data, and our physical implementation will be to build an RC car and find a microcontroller to use. We found one. We are planning to use the Arduino and then build it on. Our system, this is just a system overview. It's split up into 3 hardware components: the vehicle, the microcontroller, and the database. The vehicle will be using a navigation AI, which is directly communicates with the microcontroller to make sure for like a turn change, for lane change, for just any type of action that the vehicle must take. The microcontroller will be using Carla and Dragonfly. Oh, the navigation AI will be using the simulated data from Carla and the local positioning data from the Dragonfly, which is also being continuously input into the database, which we have set up using MySQL. The functional decomposition is the level 0 is what our project is at its core. At its core, it's a smart navigation system, which its input will be the driver's vehicle data, and the output will be an analog signal to determine whether or not an action is safe or not. So based on the path that the vehicle wants to take, it will then output a signal that whether or not a lane or turn change is safe to be made. Our level 0 is made up of 4 components. These components are the sensor. Sensor will be used for image recognition and collision detection, just in case the vehicle cannot use something from the vehicle does not take into account something from the database, such as pedestrians or stop signs. The Dragonfly will be our local positioning system. The path planning algorithm will use the surrounding vehicle data and the driver's vehicle data to create the most optimal route, and the database will be continuously updating the navigation AI and can be continuously updated by Dragonfly. This is just a diagram showing level 0. As you can see, the 2 inputs are the internal autonomous vehicle data and the route request from the user's vehicle, and it will then output the most optimal route. This is showing how every module works in the smart navigation system. So the Dragonfly data will be continuously be updated into the database, which will then go into the path planning algorithm. The sensor data will also go to the path planning algorithm. The path planning algorithm will then take into account both these input data and create the most optimal route as the output. This data flow diagram just shows a basic example of how the vehicle would go about making a action. So here you see that the vehicle is making a navigation request on the navigation AI, which is continuously being updated by MySQL database. It will then, the navigation AI will also then check to see if it's safe to make based on the sensor. The sensor will then confirm whether or not a pedestrian or a sign is in the way, and if everything is safe, it will confirm by outputting a logic 1. And once the navigation AI has determined that the action is safe to make, it will approve the request. This is a use case diagram just showing how a vehicle would go about not colliding into another vehicle. So as you can see, vehicle 1 and vehicle 2 are continuously updating their local positioning, their position, their speed, their acceleration, their dimensions onto the navigation. I was directly communicating with the MySQL database. The vehicle 2 then receives vehicle 1 data and determines that it is not safe to make the action as it's going to crash into vehicle 1 if it does.
So specifically with our hardware design, we've put sensors in all 4 directions of the car, front, back, and left and right. These are going to be infrared sensors, and they're based on what we call a stop, slow down, go system, which will be produced by a green, yellow, or red LED for stoplights, easy to see. Depending on the distance parameters you put on our IR sensors, it'll tell the car as an output to slow down, stop, or to keep going and nothing's interrupted. And then also, as an addition, we'll put sensors that'll be able to tell it if an object's coming from the left to turn right or move to the right, have an inverter logic gate for that. And here's a demonstration for our hardware. And we might have the same problem as the last week back before with the medium plan.
So for this demonstration, basically we put an LED onto a breadboard and integrated all the sensors into it with logic using the Arduino microcontroller. So the LED outputs a state, and the state is it's in either 2 states in this case. It's stop or go. So if one of the sensors is tripped, or 2 of the sensors are tripped, it automatically changes the state of the LED on the board, so it shows the logic and the collision avoidance capabilities once we actually have the vehicle.
Yeah, so as Jack just said, he's just going to put his hand in front of the sensor and it's going to give an output to a state, a main LED that's on our board. So if one of the LEDs on one of these sides turns a different color because an object's in front of it, the main state on the microcontroller will change and be affected.
I just wanted to add something. So we first originally tried this with ultrasonic sensors, but we saw that there was actually latency problems, and we actually had problems with detecting the ultrasonic waves coming back. So we went to infrared because it has more accurate in terms of distance since we're using light instead of sound.
This is some related theory, more related to the software aspect, including image recognition and the DQ neural network learning model that we used. So on the top, you can see the formula that actually calculates Q values. So if there's a type of reinforcement learning called DQ learning. It basically takes an environment's values and then it takes actions and trains by doing actions and then updating its Q values based off rewards and rules that you'll set in advance. So you can set rules like if it collides with another object that's negative reward, and or if it crosses over a lane, that's also negative reward. And if it's maintaining a speed limit, then it will be positive reward. So basically, this is the underlying equation towards that. There's also image recognition for object detection. Just on the left is a simple noise reduction using a Gaussian kernel that will basically just provide a simple blurring of the image that will allow it for to get rid of any like impurities or like very minute things that are not required. And then there's a sole edge detection calculation, and that's for feature extraction that will give you the edges that can help in object detection for like stop signs and pedestrians. And then for the software breakdown, we have MySQL database. That's what we've been using to update the input from the vehicle sensors, including location, speed, acceleration, and steering direction. And then Carla is an open source autonomous vehicle research simulator. And basically, that allows us to optimize our system, our network. And it has many resources, it has sensor libraries, it has weather variations and different maps, and many other features. So basically, for our self-driving car, design, we utilize OpenCV for the image processing, and then we trained a deep Q learning neural network that has learning rules and rewards that trains the vehicle to remain in the lane, stop, and avoid collisions. Alright, so right here, that's just the neural network code. And that's Carla's engine. That's the full map, but what we're going to show here is just a simple predetermined route that a car is going to take and stay in lane and stop at a stop light. And right here, this is just, Carla has like a built-in HUD where you can like change the features that you want to be showing and tracking. So we track the FPS just for, and also the steering direction and the speed. And then upcoming, it's going to approach. It's not a stop sign. It's just that's just like a for right here. That's it's hard to see, but there's a stop sign, stoplight that's red right there, which is why the vehicle stopped, and then it takes a while, but when it turns green, then it'll start moving again. Yeah. Yeah, and then it turned green and it started moving again. But
So as you said before, we went through some iterations on hardware design. Jack said how we started with ultrasonic sensors, but we found that there was a latency between the transmission and receiving of the data. So we went to IR sensors on all four sides. Also, which was shown in the demonstration, that state LED, that one main LED, which gets changed by any variable around the car. That was something we added onto the project. And the directional change, if something comes from the left, moving to the right, and vice versa from the other, was something added on later on. And then as for testing, we have to do unit tests, acceptance test, integration tests. Unit tests specifically for our code, making sure each piece of code is correct and works properly in Carla. And then integration and acceptance tests for the entire project and how we can bring it to the real world. So we won't go, we'll just say very brief. This is just an example of ours with efficiency, our acceptance test, and how it works, but we'll just kind of go brief through all these. Just go through.
So yeah, we have to make sure that our project is scalable, because we don't want to actually make a real life model. Just like the Carla map, we're going to try to scale it down, and that's why we're going to be using Dragonfly, as it's a local positioning system that is scalable down to inches.
So for my acceptance test, I did security. So basically, I was just I researched some methods for security. We plan to use AES-256 encryption for all of our data going in and out of the database. So anything going over wireless communication channels that someone could sniff, for example, like packet sniff. So basically, what we had to do is we had to choose the security method, and then we had to test it. And we plan to continue doing the testing and integrating the security method next semester.
Marketability, it's the same thing with us. We're kind of scaling it to a real world level, being able to convince the customers that this is a safe alternative to the actual driving that we have nowadays, and bringing it to the real market. Here's our Go No milestone. Milestone. We had 3 things we really wanted to accomplish this semester for the 40%. One of them being the physical design for our RC car, which we have the basic design that we said before will be 3D printing over the winter intersession while the labs are available. Our database setup, which we have a basic database right now, taking inputs from our sensor hardware and collecting and allocating data to specific spots to use. And being able to make a simulated autonomous driving setup in Carla, which we just demonstrated before we got going, and for us, we find it's complete.
Yeah, so for the physical design, as we said multiple times already, we'll be using CAD to 3D print our car. So this is an example of a template car that I found online. But I also did play around with this in CAD and saw that you could insert holes into the 3D printing design, so we could make holes for our sensors and choose the sensor locations as necessary. And this is just a basic picture of that red board that we were demonstrating earlier. So that has the all the directions, has the infrared sensors in all the directions and the onboard microcontroller.
And so for our project schedule, we had 4 main items we wanted to hit. Our first being proposal and initial research, which we've done, which that's complete. Now we're in the middle of demonstration and now software testing, running the neural network, and doing Carla. And so that's where we hit. By the end of winter, we should be done with our demonstration and building of our track and our hardware and all testing, all software from there on. And this is just a visual of that same diagram, the percentages and dates. As for cost, most of our costs are going to be within our microcontroller sensors and cars themselves, the camera sensors and software that we're going to be collecting. After all, we found it to be $239. Right now, we haven't hit the max and all that cost, so actually we're probably going to go under that, but we should be staying on budget pretty well. As in conclusion of future work, as of today, like we said, we've finished our simulation in Carla. Not finished, we're working on it, but we've hit our milestone for today. We hit our basic hardware design for each car. We'll be now implementing that over the winter. And we created a basic database for the data that we're retrieving from our cars. Moving forward, creating route algorithms where vehicles can communicate with each other and detect routes and make sure they don't interfere or collide with each other is the next steps moving forward. And 3D printing cars, as said, is the next steps.
So one of the codes that we were made aware of for our project was the 1968 Vienna Convention. This convention set up some safety standards for global traffic systems. This safety standard basically states that while a global traffic system can support a driver, it cannot completely take over all functions without possible interference. This means that level 5 autonomy is actually illegal, and so we're not gonna try to go for that. We are trying to get as close to level 5 autonomy while still allowing the driver to take charge whenever they need to. We will also be looking into, we'll also be taking into consideration our copyright laws and give credit to any work that we use to come up with any conclusions or a reference. Traffic and safety laws.
As for ethics, the biggest ethic question we have is our safety of our pedestrians and customers, which is our number 1 priority. It's the basis of our entire project, so that's something I will make sure to achieve very safe methods. Being honest and open to the public, not trying to keep any information from them, making sure that everything is on board with customers are okay with it, the different manufacturers and compliance programs are okay with it. And maintaining technical competency, undertaking technological tests for others, like qualified people, expertise, only giving the information to those who can use it and are qualified, not compromising any of our information. And to take real criticism of our work, getting feedback from customers, and using that for future progress. Here's just a list of our references, and that is all. Any questions? Yes?
Your vehicle communication devices are infrared. How would they operate under very fine conditions? Would this break down without some sort of backup like ultrasound?
So actually, that's a really good point to consider. We were just getting the basic software hardware aspect of it, but yes.
You need a backup or an additional means of communication and detection, correct?
Yes. So we haven't considered whether in our physical design yet, but now that you bring up that point, I will definitely be considering it for the next one. Ultrasonic will definitely be part of that. The reason we went with infrared, though, as I said, is because the speed of light is a lot faster than the speed of sound, and it can react faster to any of the situations that a car will be presented in the constantly changing traffic situations. Any other questions? Thank you.